This is us on a regular Monday. Project Evaluation Sync. Seems like nobody expects anything out of the ordinary. But then, this happened. An earthquake, epicenter less than 120 kilometers where we were sitting. The probability of an earthquake of that magnitude at that location and at that exact moment, while we happened to be in the room and intentionally set the camera for recording, that's roughly 1 in 7,920. A rather unlikely event, to say the least. But that number is nothing compared to this next scene, what we call the quantum Russian roulette. What we can tell you right now is the odds of walking out of this alive, if you run it 13 times consecutively, is this. Then this, the famous Schrodinger's cat experiment. Instead of you looking up into the box and seeing that the cat is either dead or alive, we let you be the observer outside the simulation, running in real time. What you'll see is this. That's just a little teaser of these experiments that we'll showcase in this video. All of these will all point to the same question. The answer, according to our best understanding of physics, is the one nobody wants to believe. You do not die. At least, not from your own perspective. So, welcome to this special documentary about quantum immortality.
For most of human history, the universe makes sense. Objects fall when you drop them. Planets and their moons move in predictable orbits, and cannonballs follow specific trajectories through the sky. In 1687, Isaac Newton published the Principia Mathematica and unified all of it. 3 laws of motion and a law of gravity. The same rules that explained an apple falling from a tree also explained the moon orbiting the Earth. And physicists at the time believed they were done. And then in 1927, a British physicist G.P. Thomson fired a beam of electrons through a thin crystalline film. The crystal acted like a series of extremely narrow slits. If electrons were simply tiny balls, the pattern on the detector screen behind should have been a simple cluster. What appeared was an interference pattern, the exact signature of waves and not particles. That same year, Clinton Davison and Lester Germer confirmed it independently through crystal diffraction. The electron was not a particle pretending to be a wave, or a wave pretending to be a particle. It was somehow both. And the question physicists were left with was not just how. It was, what exactly is an electron when nobody is looking at it?
From here and even today, the weirdness of that question has spread beyond the lab and into the culture. People began connecting quantum to everything. Quantum healing, quantum crystals, even quantum consciousness. If reality itself is uncertain at its foundation, then surely anything is possible.
So the universe turned out to be nothing like Newton described. At the smallest scale, particles do not have definite positions until you measure them. They exist as clouds of probability.
So it's almost as if the electron is kind of like a wave when you're not looking at it, but it's a particle when you look at it.
By this point, quantum weirdness had been accumulating for decades, 3 decades to be exact. So in the late 1920s, Niels Bohr and Werner Heisenberg developed what became the standard equations. It goes like this. Before you measure a particle, it exists in superposition, all possibilities at once. The moment you measure it, the wave function collapses. All the possibilities snap down to one definite outcome. That is what you observe.
Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. Run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you.
Richard Feynman used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys because I don't get it and you don't get it and Feynman doesn't get it.
Mathematically speaking, it worked beautifully. But 3 questions were still a mystery. What actually causes the collapse? Where does the collapse happen? And what is the particle doing before you look at it? These questions were debated at a series of conferences in the late 1920s. most famously in Copenhagen, Denmark.
So this is the Copenhagen view. Sometimes it's simplified into the shut up and calculate interpretation. It works, don't worry your pretty little head about how and why. The Copenhagen view says we can't say anything more about the quantum world beyond what we can measure and observe. What's going on behind the curtain before we look, we have nothing to say about it.
A lot of scientists were not happy with that, including Schrödinger himself. So in 1935, he designed a thought experiment, specifically to show how ridiculous the Copenhagen interpretation actually was. We have a cat, a sealed box, and a radioactive atom with a 50-50 chance of decaying in an hour. If it decays, a chain reaction kills the cat. If not, the cat lives. According to Copenhagen, before you open the box, the atom is neither decayed nor intact. It is both, which means that the cat is officially both alive and dead at the same time. Schrödinger was not saying this was a cool idea. It was like saying, look at what your theory is forcing us to say.
This ingredient, when it is left undisturbed by outside influences or measurements, evolves in a smooth, deterministic way called the Schrödinger equation.
And Schrödinger was not alone here. Albert Einstein had the same reaction. They were actually exchanging letters about this in 1935, the same year that the cat paper came out. Both physicists felt that quantum mechanics, for all its predictive power, could not be the final answer.
Einstein put it this way: God does not play dice with the universe. He meant that reality, at its foundation, cannot be random. There has to be something underneath the probabilities, something deterministic. The dice have to land somewhere for a reason, not by pure chance.
And then, fast forward 2 decades later, a grad student at Princeton was about to propose something far more controversial. His name was Hugh Everett. Not the first, not the second, but Hugh Everett the third. Anyhow, he asks, what if the wave function never collapses at all?
What if, instead of all the possibilities snapping down to one outcome, all of them actually happen, as in really happens, in real, physical universes? Going back to this, we arrive at another interpretation of quantum mechanics. In many ways, it can be seen as an extension of the Copenhagen interpretation, except this one involves a branching reality.
That's right. Instead of one outcome, the universe actually splits. Every time a quantum event has more than one possible result, reality does not choose. It duplicates.
Neither of you knows about the other version of you. Each thinks they live in a single definite reality, but the bigger picture embraces more than one world.
The idea is that distinct branches will never affect each other in any way. It's as if they have become part of separate worlds. That is why Everettian quantum mechanics is called the many worlds interpretation. You can think of this like a movie. When you press pause, you see one frozen frame. That is the Copenhagen view. And then you press play, and the story continues in a single direction. But Everett said no. If you press play, the story branches, not into two possible futures, but into two actual ones. You just cannot see the other because you are locked inside your branch. And so the idea is that every quantum event and every interaction splits reality again. The universe is basically a tree with an infinite number of branches growing every quantum moment.
When Hugh Everett came up with this idea, it was the most conservative interpretation of the mathematics. Yes, it seems ridiculously uneconomical to have all these worlds, but the math, if you just take it at face value, this is what it seems to say. How do we transition from a theory that describes a fuzzy haze of possibilities to the single definite reality when we make an observation? And nothing in experience suggests there's anything but one single definite reality. And that was a conundrum. Experience shows one reality. Quantum mechanics speaks of many possibilities.
Measurements in that realm.
Right. That's right.
Now, if this is true, if reality genuinely branches, and if there are copies of you in other realities experiencing different outcomes, then something very strange follows.
So we are going to stage the cat experiment in real life.
And to show you what that is, we're going to need to leave the studio. We're going to a paintball field.
So here we are in this beautiful paintball arena, and we're going to do the quantum Russian roulette experiment. Let's see how it goes.
Every electron has a property called spin. You measure it, you get one of two results: spin up or spin down.
Now we take that electron and we wire it to this paintball marker. and we'll have Sam, our video producer, to point this directly at me. If electron measures spin up, it's an empty chamber, and I walk away. If electron measures spin down, the gun fires, and I die. So it's either your life or your death. The thing is that before the measurement, the electron is in superposition, spin up and spin down at the same time. And because the gun is wired to the electron, the gun is also in superposition. There is a version of me that just got hit, and there is a version of me that just heard a click. According to many worlds, both versions are real. Both actually happened. The universe did split into two. One branch where you're dead on the ground, and the other branch where you are standing here, very much alive.
At least in this universe, I'm still alive.
So which version do you experience? I want you to really think about this. To experience something, you need to be conscious. A dead person is not conscious. So the branch where you die, you will never find yourself there. It's not that you escaped it, it is that there is no you in that branch to experience anything at all. The only branch you ever find yourself in is the one where you survived. Now do it again, and again, and again, and again. We pull the trigger, universe splits, one version of you dies, one version of you lives. And once again, you can only be in a branch where you are alive.
From the outside, from where the audience is standing, the odds of surviving all 50 rounds in a row are roughly 1 in a quadrillion. That is a number with 15 zeros.
But the probability of that particular you that survives is 100% every single time.
This idea is called quantum immortality, formalized by physicist Max Tegmark. And he was very precise about the conditions. One is that the randomness must be quantum, a genuine quantum event, so the experimenter actually enters superposition. 2. The gap between measurement and death must be shorter than human perception, approximately 1/100th of a second. You cannot have time to realize the outcome before it happens.
3. It kills, or it does nothing. We're not talking about injuries or what have you, it's either instant death or a click.
If all of these 3 conditions are met, Max Tegmark argues that you will always find yourself alive, because every branch where you die is a branch where there is no you left to notice.
The many worlds allows a world in which anything compatible with physics is realized. Us living to 100, 200, 500, 1,000, I don't know that there's a law of physics that prevents that can't happen.
The proof only works in one direction, inward. You will always experience survival, but nobody else will. And needless to say, this is a thought experiment, so just keep it that way.
From the outside, from where everyone else is standing, the experiment plays out exactly the way you would expect. A person pointing a gun at their own head. In most branches, they watch you die. In one branch, the astronomically unlikely one, they see you walk out. And they will not call it proof of anything.
And that, I think, is the trap. The most profound evidence in the history of physics, and you are the only person who will ever know it is real. To everyone else in almost every branch of reality, this life is non-existent.
It really is strange. And it's like the bump under a fitted carpet. You can shove it behind the sofa, behind the TV so it doesn't show up. But that bump is somewhere. You can say that bump is many worlds branching out. You can say the quantum wave function spontaneously collapses. You know, there are lots of ways of explaining. But that weirdness is there. Where you leave it, where you decide the weirdness originates, is what we can't agree on.
There's one more experiment that we're going to showcase. We certainly didn't plan for this, it just happened while the camera was already running. This was a real earthquake. We were doing a routine project thing and then the ground started moving. The epicenter of the quake was less than 120 kilometers, a 4.6 Richter scale quake right beneath us. Now here's the thing. The probability of an earthquake of that magnitude at that location and at that exact moment, while we happened to be in the room and intentionally set the camera for recording, that's roughly 1 in 7,920. A rather unlikely event, to say the least. But we walked out, and nothing collapsed on us. We got lucky, right? Or did we? Because if you take many worlds interpretation, what happened that afternoon was simply a selection. There are branches of reality where the building did not hold, branches where we did not make it to the door in time, or where this documentary does not exist because the people making it are gone. Obviously, we're not in those branches. We're here and talking to you right now. And that is exactly what quantum immortality predicts. The idea that you're always the survivor. Always. Because the branches where you die are the branches where there is no you left to experience anything.
But if you ever tried to prove this to someone else, you would immediately fail. Because from their perspective, you are just a person who got lucky once, and eventually their luck runs out in the branch they happen to be in.
Quantum immortality, if real, is the loneliest fact in the universe. You survive, and you know why, but nobody will ever believe you.
We've been talking about guns, electrons, and collapsing buildings. But in 2001, philosopher David Lewis took the discussion in a different direction. His point was very simple. The entire universe is already a quantum system. Every atom in your body, every molecule inside your cells. All of it is governed by quantum mechanics.
And so if quantum mechanics produces branching, then branching is not waiting for some physicist to set up an experiment. It is already happening in you.
If you take the many worlds approach to quantum mechanics to heart, it is saying that clearly we are compatible with the laws of physics because we're here, existence proof.
Right.
And if you take the many worlds seriously, then we were guaranteed to live in some world in this grand collection of many worlds. Now, in some sense, this world is incredibly unlikely within the panoply of possibilities.
Think about every close call you have ever had, the car that almost hit you, the illness that almost got worse, or the moment where things could have gone very differently.
So according to David Lewis, in some other branch of reality, it did go differently. You died, and your story ended. Now, Hugh Everett also believed all of this. He told colleagues that many worlds guaranteed him immortality, that his consciousness at every branch point would follow whatever path does not lead to death.
The tragedy of Hugh Everett is that the world's rejection confirmed something he had already decided about himself, which is that none of it particularly mattered. Niels Bohr was unimpressed, and so the science community moved on. And Everett, rather than fight for the theory that would eventually be recognized as one of the most important ideas in the history of physics, he took a job at a defense contractor where the mathematics was classified and nobody asked questions about the nature of reality. What followed in his personal life, the smoking, the drinking, and the slow physical decline, looked from the outside like a man falling apart. According to his son Mark, Everett seemed to find it all philosophically consistent. If the many worlds interpretation was true, some version of him was perfectly healthy in another branch. What happened to this particular body in this particular world was a detail he had already made peace with.
He died of a heart attack in 1982 at 51 years old. 14 years later, his daughter Liz took her own life. In the note she left behind, she wrote that she hoped to end up in the same parallel universe as her father.
Schrödinger was just confused. I mean, he understood why he was confused. I mean, he was absolutely on the ball. But lots of people were confused.
Everett was so certain he was not confused that he built his entire life around that certainty. It cost him everything.
The thing is, even if Everett was correct, survival is not what most people imagine it to be. David Lewis was the first to work out why. Quantum immortality, if it is real, does not save you from aging. What it gives you is eternal survival, at whatever cost the physics allows.
In this life here, you don't exist.
The branches where you dodged the meteorite crash are the same branches where your cells keep accumulating damage, where your memory keeps dissolving year after year. As long as some configuration of atoms that constitutes you can still exist, you continue. But what survives may not be something you would recognize as yourself.
And that leads us to another strange idea, because if the thing that survived does not feel like you, does not think like you, then what exactly has been preserved? Is the version of you that survives still you?
Philosopher Derek Parfit came up with a thought experiment for exactly this problem. Let's imagine a teleportation machine. You step in on Earth, the machine scans your entire body and transmits that data to Mars. On Mars, a second machine rebuilds you from scratch, atom by atom.
The copy on Mars wakes up, It has your memories. It even remembers your breakfast this morning. From its own perspective, it is you. There's no sense that anything went wrong at all. But the twist is that, back on Earth, the original body is destroyed. So are you alive on Mars? Or did you die on Earth, with someone else with your memories just opened their eyes on a different planet?
Man's reach exceeds his imagination.
If there's another identical me,
Yeah.
is it me?
That's the deep question.
Wow,
That
now,
is the
now that's a
question.
consciousness question.
And I think the answer to that is yes,
No,
because
I
that.
think the answer is no.
Why?
Because we've already kind of done that experiment. They're called twins.
I think the twin answer is clever, but it misses something. You see, twins share DNA, but they do not share memories. They do not share the continuous thread of experience that makes you feel like the same person you were 5 minutes ago. So a twin is a genetic copy, but the Mars version of you is an experiential copy. Those are very different things. And this is exactly where quantum immortality either holds together or falls apart. When the universe branches, the surviving version of you has all your memories, all your experiences up to the moment of branching. From its own perspective, it feels completely like you.
But is it you? Or is it a new consciousness that just happens to remember being you? There are two ways to think about this.
The first view says you are information. Your identity is the pattern of your brain, the memories, the connections, the specific way you process the world. If that pattern is preserved, you are preserved. It does not matter whether the atoms are the same. Kinda like if you move software to a new computer, it is the same software. And under this view, quantum immortality works. When reality branches, the surviving copy carries your pattern.
It is you. So your consciousness continues.
But if you take on board the idea that you are just a collection of particles that are governed by the quantum mechanical laws, then there is enough room inside of, Hilbert space and the quantum mechanical infinity to reproduce you and to reproduce every variation on you.
Then the second view says that you are continuity, an unbroken stream of subjective experience running through one specific brain and body, in one specific branch of reality.
If that stream is interrupted, then the copy may believe it is you, but your own experience ended. What opened its eyes on the other side is a replica that remembers your life, not you remembering your life. Under this view, quantum immortality is an illusion. The branch where you die is the branch where your consciousness ends. Another version of you continues somewhere else, but it is not you doing the continuing. Philosophers have been arguing these two ideas for decades. Neuroscientists cannot yet say what consciousness even is, let alone whether it transfers.
Quantum theory as a whole is wrong. It's not Einstein was wrong. Quantum mechanics is wrong. Now, I say this very blatantly because it's a blatant topic. I mean, Einstein and Schrödinger were much more polite. They said it was incomplete. Okay, incomplete means wrong.
Roger Penrose, the Nobel laureate in physics, says that the whole framework might be wrong, that the theory we have been building these arguments on top of is itself unfinished. If we set the physics aside for a moment and just look at what Many Worlds is actually saying.
If it is true, every decision you've ever made has a branch where you chose differently. Every failure had a branch where you succeeded, the braver version of you, the one who said yes instead of no. If Many Worlds is right, that version is not just a fantasy. It exists right now, in a branch of reality just as real as this one.
Our consciousness feels singular, and this theory is saying there are many individuals in this larger realm that have your memories, that have your experiences, and they only differ from you that they saw the cat dead and you saw the cat alive.
Your consciousness feels like one line, one set of choices. But if this theory is right, you are not a line. You are a tree, and every branch is as real as the one you are sitting on.
So here we are. Quantum immortality says that you might never die from your own perspective. But it also says the proof is invisible to everyone else. And the survival may not be graceful. And the you that survives may not be you at all.
All things compatible with the laws of physics are realized.
Still a real, wow.
And that includes a version of you that walked out of the box.